All right, time to get started on our 10 a.m. press conference. Opportunity rover headed for something different on Mars with help from orbit. We'll have three speakers in this order. Janice Bishop, with the CRISM, she's a CRISM team member from NASA Ames Research Center, Moffett Field, California, and from the SETI Institute in Mountain View, California. Ray Arvidsson, he's the Mars Exploration Rover Deputy Principal Investigator and CRISM team member. He's from Washington University in St. Louis, Missouri. And our third speaker will be John Callis. He's with the Mars Exploration, he's the Mars Exploration Rover Project Manager. He's at NASA Jet Propulsion Laboratory in Pasadena. Oh, and just I wanted to ask the speakers, please, when you're doing your pointing, use the mouse so we have some people on the web, they can follow along. Thank you.
Good morning. I'm going to be talking about using orbital spectrometers to map hydrated minerals on Mars in order to gain information about geochemical environments on the planet. Hyperspectral imagers such as CRISM and Omega have been collecting light reflected from the sun across hundreds of wavelengths in the visible and infrared region. CRISM is the compact reconnaissance imaging spectrometer for Mars on NASA's Mars Reconnaissance Orbiter, MRO. It collects images about 10 kilometers across with pixel size of about 18 meters. Omega is a similar spectrometer on ESA's Mars Express. We humans use our eyes, use the colors red, green, and blue with our eyes in order to project images. CRISM has 544 channels and projects hyperspectral images in a similar fashion. Each of these spectra has dips and peaks in reflectance, and we use these with minerals to make a spectral fingerprint of minerals with collections of peaks and dips in order to identify these different minerals on the planet. The first slide shown up here shows a map with clays in green across the planet, and you'll notice there are a lot of small outcrops of clays, particularly across the equatorial regions. These clays are revealed on the surface where ancient rocks are exposed. Most of the clays formed about 4 to 4.5 billion years ago and probably in long-standing neutral waters. Hydrated sulfates are a little bit younger, formed about 3.8 to 4 billion years ago and in a more acidic environment than the clays, and would not necessarily have needed long-term standing liquid water to form. Before the MER mission, we didn't know that the surface of Mars had clays and sulfates. The rovers have been discovering sulfate minerals at both landing sites. About the same time, Omega discovered widespread clays and hydrated sulfates across the planet. There are small clays there are small outcrops of clays in many sites across the planet, and there are larger outcrops of clays in two main regions, near Marth Vallis and near Nile Fosse. And in a few locations, we've seen recent clay formation, perhaps related to impact processes. Understanding the mineralogy on the planet can constrain the geochemical environment. For example, the ancient clays that are detected across most of the planet are an iron-rich smectite called nontronite. This likely formed from volcanic ash in long-standing liquid water. Another kind of clay, aluminum-rich clays, likely formed through leaching. Other kinds of clays called serpentine and prehnite probably formed through alteration of olivine or impact processes. Sulfates can also tell us information about the environment, including information like the types of cations in solution, the pH level, and perhaps the temperature regime or type of aqueous conditions. Understanding all of these geochemical parameters can help us identify sites on Mars that could have provided habitable environments for microbes. There's been a disconnect in the past between orbital and landed missions due to different spatial scales, rock coatings and dust, and different kinds of instruments. Spatial resolution is inherently different for surface and orbital missions. In the past, orbital spectrometers have had spatial scales well beyond that possible with rovers. CRISM currently measures a pixel size of about 18 meters. Omega has much larger pixel sizes. Generally, when we're trying to detect minerals on the surface, we want to collect mineral identifications from several neighboring pixels in order to be sure about our mineral detections. That means we need usually about 50 to 100 meters in order to be 50 to 100 meter size outcrops on the surface in order to be confident with our mineral detections. Ray will be presenting today some new advances with CRISM that are enabling us to reduce the size of rock outcrops that can be detected from orbit. In the second slide, and let's see, there we go. Here in the second slide, we have the ancient crater terrain in the south. This is a map of the Meridiani region, and the Mars Exploration Rover Opportunity is investigating here. The ancient crater terrain is in blue in the bottom half of the image, and the younger Meridiani sediments are in red, and the impact material is shown in green. Opportunities traversed is shown in yellow. CRISM has identified clay and hydrated sulfate outcrops in this region, and there are 3 clay outcrops shown here in dark blue. Along the rim of Endeavour Crater, CRISM has also identified some clay and hydrated sulfate outcrops that are on the order of 1 kilometer or so less across. Another thing that makes orbital remote sensing tricky is rock coatings. CRISM and Omega collect light reflected only from a thin surface of the rock. If there's lots of dust or a thick coating on the rock, then we'll likely only be measuring the properties of the coating or the dust. If there's a thin coating of dust or a thin layer of dust or a thin coating, then we're likely going to be measuring a combination of the coating and the rock together. So on the surface, we have the advantage of the RAT tool. And the next slide shows a small diagram. This is an example rock on the surface of Mars, where we have a coating on the rock and dust on top of that. And on the rover, the RAT can brush off the dust and grind through the coating and reveal the fresh rock underneath for the instruments to measure. Unfortunately, we can't do this from orbit, but what we can do instead is look for fresh rocks in crater environments. Another difference between orbital and space missions is the type of instrument used. Reflectance and emission spectroscopy tell us about mineralogy from orbit, and X-ray diffraction can tell us about mineralogy on the surface and will be used in future missions. Opportunity can measure a variety of things, including abundance of elements, bonding of iron atoms in the mineral structure, and magnetic properties. We are all hoping that Opportunity's upcoming analyses of the outcrops detected by CRISM will increase the synergy of orbital and landed missions. CRISM has recently detected a small outcrop of hydrated sulfates in the Meridiani region near the traverse of Opportunity. The exciting news today is that Opportunity will soon be able to perform detailed geologic field investigations where CRISM has discovered this outcrop from orbit. Ray is now going to provide some more details about these interesting rocks that Opportunity is about to approach. Thank you.
Well, good morning. I want to introduce you to a developing story. We've traveled, as of yesterday, 26,430 meters since we landed in January 2004. And of course, what's coming up in January 2011 is the 7th year anniversary. I had no idea I'd be standing up here in 2004 thinking about doing a presentation about Opportunity results in December 2010. This vehicle is so far out of warranty, but works so supremely well, and John will be telling you about some of the logistics. What I want to do is come back to the science, and Janice mentioned that there are ancient rocks that seem to have formed in a pretty neutral pH, water-rich environment, the clay minerals, and Opportunity is poised in about 6,000 meters to get to those rocks on the rim of Endeavour, but Today, we're right at the rim of a fresh impact crater about 90 meters across called Santa Maria, which exposes rocks that are hydrated, which we haven't seen on any of the CRISM data covering any of the locations that Opportunity has traversed. We know that the rocks that we've seen with Opportunity formed in an ancient drying out lake environment where the mud would form, sandstones would form by wind, groundwater would come up and cement and alter the materials, but we've never seen the fresh rock from orbit. We're about to get there in January. This shows you the 26,430 meters worth of traverses as of Sol 2450, which I think was Tuesday, and we were just looking at the back of the room at the downlink coming down as we speak. We're right at the western side of this crater called Santa Maria. Every place that we've been to looked with CRISM in terms of the spectroscopy suggests that we're looking at dehydrated coatings or rinds on the surfaces of rocks. This is the first time, because it's a fresh impact crater, where we may be able to see rocks that haven't been weathered or coated in the Mars environment. So we can do detailed field verification and detailed field investigations. It's also nice to have a program of Mars exploration in which the orbital assets and the landed assets work synergistically for science. And as Janice mentioned, we've been using CRISM in a special mode. The way CRISM operates, it has a gimbal with the optics. And as we're coming over a site, that gimbaled system rotates the optics to produce the center frame. They're 18-meter pixels, usually cheek to jowl. And what we've done is to modify that gimbal pattern so we get oversampled information in the along track direction. And that allows you to sharpen down to a smaller size, typically anywhere from 6 to 10 meters per pixel in terms of backing out the information. That's allowed us to actually resolve some of the spectral features on the outcrops of the rim of this small crater. You can also see off in the distance in the lower right those peaks that we call Cape York, Solander Point, Cape Tribulation. Those are parts of the ancient crust of Mars sticking up as part of the 22-kilometer diameter Endeavour Crater. As soon as we're done with Santa Maria, it's going as fast as we can across those plains to get to those ancient rocks, and I'll show you those were where the clay minerals are exposed. So this is incredible. We're going to look at the ancient rocks during the wet period when we get across the plains, but within the next few months to weeks, we're going to look at hydrated sulfates that seem, based on nature's drill, that is a fresh and impact crater, not to have been weathered in the Mars environment yet. This is the crater, and in fact, Opportunity is poised just off the left side in the ejecta deposit, and it's driven a little bit closer, and one of the first things we'll be doing is long baseline stereo imaging of the interior, because we've never seen a crater this fresh, this big. You know, it's roughly the size of a football field. And it's an impact crater. But the two circles, the red circle, the southeast rim, and the blue circle, the floor, those are areas for which we've been able to sharpen and remove some and display some CRISM spectra that pertain to mineralogy. So these are the two spectra. And what we're looking at on the y-axis is the amount of sunlight reflected, and the x-axis is the wavelength. So these are infrared wavelengths, but it's still solar reflected. So it's from about 1.2 to 2.4 micrometers. And as Janice knows very well, that bottom curve is very indicative of a pyroxene, the iron in pyroxene. It's called an electronic transition feature, and it's very diagnostic. Geologically, it makes sense, because from orbit, what you see is this dark material is streaming out from the crater, and it's probably basaltic sand that we find in many places sitting on top of the sedimentary rocks that we've been investigating. The interesting spectrum is the one for the southeast corner, and that dip, just longward of 2 micrometers, is very, very suggestive of a monohydrated sulfate, like a kieserite, which is magnesium sulfate with 1 water in the crystal lattice in the cell. Is it real? Well, there's a question mark there on purpose, because we'll be there in a few weeks and we'll do detailed measurements to field verify or validate this identification, look at the other minerals present, and put it in a geologic context. If this is really the drying out period of Mars, as opposed to the wet early clay period, you know, the minerals in the geologic context are all important in terms of identifying what's been going on. Where is Opportunity? Here's where it was yesterday at 10 o'clock PST. It's It's looking at the rim from the west in the ejecta deposit, and we're looking toward the southeast. And in fact, off in the horizon, those little bumps they're parts of the rim of Endeavour. Turns out it's the far side, so it's about 20 kilometers away, where we'd be going. You can't see it from where we are, but you can see that there are bright rocks exposed within the ejecta deposits of this crater. Those are the rocks we're after. But the best exposure from CRISM is down to the southeast. So after we're done the imaging experiment to really pin down the morphology and topography of this crater, we'll wind up in January, February, doing long-duration measurements over that interesting pixel. It's the first time we've used a mineral detection from orbit to tactically drive where a rover should go. So we're going to a particular pixel to make the detailed measurements. A look ahead. These are some of the rim segments of Endeavour. The closest position to us is Cape York. So the blue areas are the rim segments. They're mainly basaltic materials, but look to the south, and the green represents a dominance by clay minerals. This is work that's been done by James Ray using some older CRISM data. We now have oversampled data that we're working to really pin down other locations where there are clay minerals, likely in Cape York, for example. But also, if you look at the area called Botany Bay where there's hydrated bedrock, from the older data, James Ray has been able to say that there are hydrated sulfates and generally water-bearing minerals in this area. We have to cross that terrain to get to the ancient crust, and we'll make measurements along the way that will further kind of build the case for what's happening in this massive transition in conditions from the ancient crust and the clay minerals, neutral pH, to the younger materials, the layered sedimentary rocks that seem to be sulfate-dominated. And just to kind of whet your appetite a little bit, what we've done, so we've been moving toward the rim, is using our PanCam on the mast, the high-resolution imager, to take one after another at the same time within about 30 minutes, going back and taking repeated images. It turns out they're slightly offset, and you can use that information in what's called a super resolution mode to sharpen the information. So this is off looking at Cape Tribulation. It's about 100 meters high. The slopes are 15 degrees, but we know how to climb on these. So invite us back next year or thereabouts, and we should be talking about clay minerals on the rim. So the beauty is, you know, we're going on the 7th year anniversary, and we're poised to really pin down the fresh mineralogy of this period of drying out of Mars. And then after that, 6,000 meters, and we'll be to the rim for the ancient materials. And if we're lucky, we'll get up onto the materials that indicate a much higher water-to-rock ratio, a much wetter period of time, and probably more neutral pH conditions. So who would have thought, you know, in January 2004, we'd be able to talk about this in December 2010. But we have to get there. So John, who's the project manager, will tell us about the status and health of the vehicle and a prognosis for 6,000 meters plus.
Thank you, Ray, and good morning, everyone. As Ray mentioned, next month will be the 7th anniversary of what was to be a 3-month mission. You know, the great thing about rovers is that an extended mission is like a brand new mission. Because they can drive, they can go to new terrains, new unexplored regions, and expand not only in time but in distance what we're exploring on the surface of Mars. In their almost 7 years on the surface of Mars, Spirit has traversed 7.7 kilometers, and as Ray mentioned, 26.4 kilometers for Opportunity. Combined, the two rovers have returned over 250,000 images from the surface. Now, Spirit is silent right now, but Opportunity is in good health, but showing some signs of age. Well, first, let me talk about some of the instruments on the rover. We have the miniature thermal emission spectrometer. That instrument suffers from a dust contamination that occurred during the last major global dust storm that Opportunity had to survive. We've been trying techniques to try to mitigate that. There's also an additional anomaly within that instrument because that instrument has been subjected to colder temperatures than it was designed. The Mossbauer spectrometer, which has a radioactive source, has a much weaker source right now. We are now probably 10 to 12 half-lives later in that source. So what was originally a half-hour integration for the instrument now takes a week or more to get the same kind of measurement. The robotic arm, the instrument deployment device that we have, the freedom arm on the rover. It has arthritis in one of the joints. It's restricted in that motion, but we can still use the other 4 joints to adequately place the arm. We can actually turn the rover to get that final degree of motion in positioning the robotic arm instruments on targets that are of interest. On the end of the robotic arm, we have the rock abrasion tool. That tool was designed for only 2 grinds on the surface of Mars, and now some dozens or more grinds later, we still have some life on the diamond tip bit that it has. So we have a few more grinds left in it. We'll be saving that for probably a grind here at Santa Maria Crater, but we'll preserve the balance of that for when we get to Endeavour Crater. It also has a brush that was mentioned, and we can still brush many targets with that. Our cameras are in excellent shape. This is a visually rich rover. The cameras are still 20/20 vision all around, and so it's producing these spectacular images that you've seen here. Probably the most important instrument that's of interest to us right now is the mobility system, the drive system on the rover. Again, it was designed for only 1 kilometer, and yet we've gone 26 kilometers, so we're well past warranty on that system, and we are seeing signs of age and wear in that system. So we're trying to do things to mitigate that. So one of the things we're doing, the main thing we're doing, is we're driving the rover backwards. You know, the rover is driven forward for most of its distance on Mars. We're driving it backwards. This allows these very complex gearboxes that we have on each of the on the wheels, these gearboxes, to wear their teeth on the opposite face. So we're distributing the wear within these very complex gear mechanisms. The other thing we do is we heat the actuators so they're warmer, so the lubricants flow more easily. And the other thing is we're resting the rover. We're allowing the actuators to recover between drives. When we explore here at Santa Maria Crater, we'll have that opportunity to rest the actuators some. So this is kind of like the senior marathon runner who, after it does a long run, will ice up their knees and take some ibuprofen to get them ready for the next long run. Because we are driving backwards with the rover, that limits some of the autonomous navigation that we can do. The rover uses its camera systems to image the terrain, to generate terrain meshes, the lay of the land, and use that information to make decisions about driving and to keep it safe as it drives. Well, because we're driving backwards, the camera, the main camera on the rover, has to look over the back of the rover. And on the back of the rover, there's a low-gain antenna mass that sticks up. And so that sticks up in the field of view. So when we're driving backwards, we actually have to turn the rover one way and then the other way to get that low-gain antenna out of the field of view. This is much like you're driving your car and your child is waving their toy in front of your face and you're dodging your head from side to side to keep your eyes on the roads. That complexity limits the extent that we can use autonomous navigation as we drive the rover. But even still, we've been able to get drives that exceed 140 meters per drive saw on the surface. So we expect that we'll actually, once we're finished here at Santa Maria Crater, be able to pick up the pace and continue driving further. So we're at the crater right now, Santa Maria. We'll be exploring, doing a survey of the crater. We'll be positioning for solar conjunction. Starting in late January and extending through to early February, the sun will be pretty much within the line between Earth and Mars, and this limits communication to the rovers, particularly commanding of the rover. So what we intend to do is during that 2 to 3 week period is we'll position the rover in one of these very exciting putative hydrate areas, put the robotic arm down on a surface target, likely the Mossbauer spectrometer, to do a long integration and leave the rover there pretty much unattended for 2 or 3 weeks. Once solar conjunction concludes, we'll then pick up the pace and we'll start this push, the 6-kilometer push to Endeavour Crater. So how long will it take us to get to Endeavour Crater? Can't really answer that. It's 6 kilometers as the crow flies. The science team has assured me that once we finish here at Santa Maria Crater, there's nothing of interest for them between now and when we get to Endeavour Crater. But of course, we are always a discovery-led mission as we go along. And linear distance doesn't translate directly into odometry on the wheels because you never go in a straight path. But I will mention that in just the last Martian year, so if we go back 687 Earth days, Opportunity has driven over 12.5 kilometers. So almost half of the odometry accumulated by the rover has occurred in the last Martian year. Going forward from here, the pace will actually increase because we'll have improved solar energy. We get to the peak of the solar energy production for the rover around mid-March. So I expect we'll make pretty good progress towards our very next exciting exploration, which is Endeavour Crater. So there's still quite a bit of adventure left for these rovers. Thank you.
All right, we'll open up to questions now. From reporters.
Hi, I'm Lisa Grossman from Wired.com. Could you go back to the picture that Opportunity took just a couple days ago of the rim of the Santa Maria crater? So where exactly in that picture are the interesting things that you're really excited about getting to, and what do they represent?
Maybe you should show the oval.
The most interesting material is on the other side.
Okay.
But that white material that you see off in the kind of midfield from CRISM looks interesting, but not as interesting as driving around the south to the southeast side. We're on the western side looking at the western rim. So what we're going to do is a whole set of measurements where we go up close to the rim, look to the interior, and make mosaics at different distances. That's called long baseline stereophotogrammetry, where we can make very exquisite topographic maps of this fresh crater. Nice. And then, as John said, we need to be positioned on the southeast rim, where the most interesting pixel is in terms of CRISM, for solar conjunction, so we can do long duration measurements. You know, if we had to, this bright material, I would opt for that. But I would wait to, since we have the time, to go to the southeast and be there.
Okay, and that one interesting pixel that you were talking about with the monohydrated sulfates is here, not at Endeavour.
There are interesting pixels at Endeavour, but they're clay minerals.
Okay.
So the monohydrated sulfate is actually a number of pixels because we've sharpened a long track, but it's about a 20-meter area.
Okay.
And it's on the southeastern rim. So
Great.
We'll be there in January.
Thanks.
Hi, it's James Dacey, Physics World. Could you talk a bit more about the kind of geology and the geological processes you're hoping to examine within the crater?
Within the crater proper?
Yeah.
Yeah, so the Meridiani Plains extend over hundreds of thousands of square kilometers, and they sit on, they're at least 100 or more meters thick where we are, and they're layered deposits that are sitting on the ancient crater terrain. And they have seemed to have formed in these ancient lake beds and reworked by wind, and then groundwater would occasionally come up and cement everything. And then it all dried out billions of years ago, and since it's been stripped down by wind, and then basaltic sand has come over, and these hematitic concretions that we see have been weathered out of the bedrock, and then there's been impact after impact after impact. And the beauty of Santa Maria, it's the size of a football field roughly, and it's geologically very fresh. So we have an opportunity to map the characteristics, the topography, the structure of a brand new impact crater, and even see if we can identify some of the impacting material that might be in the ejecta. That's from the point of view of cratering mechanics, but from the point of view of understanding the geologic history of the area, the beauty is that it appears that this impact event is so young that it has exposed craters on the rim and in the ejecta, where the exposed materials on the rim and in the ejecta that haven't had a chance to get this dust coating or this dehydration rind that Janice has talked about. So it allows us to look at the freshest materials, probably, than we've seen anywhere else.
Christina Reed, Discovery News. If the dust can build up on the rovers pretty quickly, how long does it take for dust to build up on a crater? How new is this new crater?
But the dust comes, the dust goes on the rover, right? So we didn't think we'd last 7 years because of dust accumulation, but luckily, you know, there are high wind events, primarily dust devils, that have removed dust on Spirit, certainly, and probably also on Opportunity. So it's not a simple just burial by wind-blown dust. There's some process that's been operating that kind of cements a thin layer of dust on the surface or kind of changes the mineralogy within the first few millimeters So that's enough thickness to obscure what's happening underneath from optical spectroscopy that we see from orbit. And it's a process that we don't fully understand, but we know what's on the surface is different than what we're seeing when we, with the rat, go into the interior.
So there's no estimate on time?
Oh, the age? I don't know how to do that, other than it's geologically very young.
The dust changes over time, too. You might measure a crater or a certain spot once, and then again a year or two later, and it might look different based on the dust cover.
I have a question from Nancy Atkinson, University Today. How are the Opportunity's solar panels doing as far as dust covering and energy output?
On Opportunity, the dust obscuration has reduced the solar array performance to about 60% right now, meaning that 40% of the array is blocked by dust. And so that's decreasing slightly as we go forward in time. But right now the rover is producing about 600 watt-hours of energy each day. And that's enough energy to get in a multi-hour drive in for the rover.
Yeah, Jonathan Amos from BBC News. Victoria Crater, which you've recently left, I mean, is that in essence the same sort of geological context? It's just it's weathered. It's just not as good a site to see all of this stuff.
Yeah, that's an excellent question. So we've visited, and the question is, what has Victoria Crater told us about Mars? So we've been using craters throughout the mission. You know, we landed in Eagle Crater, and that was kind of the discovery rock in terms of these cross-bedded, laminated sulfate materials that formed what we think are these ancient playa environments and reworked by wind and cemented and then altered by groundwater to produce the hematitic concretions. And then we went to Endurance Crater and did a whole set of measurements. Then Victoria. Along the way, we went to Erebus Crater, and we looked at other craters along the way. Now we're at Santa Maria. We'll wind up at Endeavour Crater. It's because these are nature's drills, right, to expose the bedrock. What we've seen throughout the history of this mission is continuing evidence that our original hypothesis is correct. And these are layered sedimentary rocks during what appears to be a drying out period of Mars, where occasionally there would be wet playas or lakes that would form mud that would dry out, wind would blow, make sandstones, they'd accumulate, and then the groundwater would come up and cement everything. What Victoria shows us is a thick section of wind-blown sand dunes that's been altered chemically. And then additionally, both in Endurance and in Victoria, the very top, you know, beneath the ejecta, but still within the intact bedrock, as a function of depth, changes some chemistry. Chlorine is depleted at the top, a little bit increased at the bottom. Magnesium and sulfur, magnesium sulfates, are enhanced at the top, not so much at the bottom. So some alteration, probably from the top down, in my opinion, has been operating since these layered deposits formed. So we're still sifting through all this, right, because we're doing mission operations and science at the same time. But it looks like we're getting more and more evidence that we're looking at these ancient Sopka playa kinds of environments. And we're adding in much more information about alteration processes. And the beauty of Santa Maria, as we said, is here's what apparently is fresh rock where we don't have to worry about coatings.
And could we have an update, John, on Spirit? And at what point do you give up on Spirit?
Well, we haven't heard from Spirit since March of this year. This is because the rover was embedded in some loose soft material and has some failed wheels that prevented us from successfully extricating the rover and positioning it for the winter. Spirit is located further south than Opportunity is, so its winters are a lot deeper and tougher, and so we've always had to position the rover by tilting it so that the solar rays point towards the north. We weren't able to do that, so the rover didn't have enough energy to stay awake during the winter time, so it's gone into a deep sleep. Our models estimated that at some point in the springtime, and we're in the springtime on Mars, that the rover would power back up. You may know that both rovers actually go to sleep each day, where they completely shut down, and then a timer wakes them up, or the rising sunlight wakes them up in the morning. So there is an expectation that Spirit would wake back up. The concern, though, is that the rover will see colder temperatures, or should have experienced colder temperatures than it had ever seen on Mars, and that it would get below the nominal operating temperature, the cold operating temperature for the electronics. So there's a risk that the rover wouldn't survive the winter. So we're listening now. We've been listening every day. The rover would autonomously wake up and talk to us. We've also been actively commanding to the rover in case it's in a potential alternate fault mode. But the period of peak solar energy production for both rovers is going to be around the mid-March timeframe. And so if we have not heard from Spirit by then, the likelihood of hearing from her beyond that starts to decrease at that point.
Other questions?
When did you start driving backwards?
Well, when we departed from Victoria Crater, which was, gosh, over a Martian year ago, we were noticing that the wheel currents in the right front wheel were starting to be elevated. You know, this again is, you know, those of you who are runners, you're noticing a cramping or a inflammation in one of your joints as you're running. And so that's when we started to explore techniques to mitigate that, because we were concerned that that might be a precursor to a failing of the actuator. We actually saw a similar behavior with Spirit right before it lost functionality in its right front wheel. And so as part of the investigation and part of the mitigation strategy, we determined that driving backwards is potentially a way to try to mitigate that, so distributing the wear as I described earlier. So since we left Victoria, we've been pretty much driving the rover backwards.
Paul Doherty from the Exploratorium. And so if Spirit had had all 6 operating wheels, you expect you could have driven out of the trap it fell into? And second, what are the possibilities of such a trap happening on Opportunity's drive?
Well, one of the contributing causes to why Spirit became embedded was that it had one failed wheel already. And if, these wheels have these large gear reduction gearboxes, so the wheels don't freely spin. So a failed wheel is locked in place. It's kind of like one of those grocery store shopping carts where the wheels jam. So when we drive the rover, we actually have to drag that one wheel. So it's like an anchor. And so that was one of the contributing factors that made the rover susceptible to this kind of collapse into this camouflage tiger trap, as we called it, these loose fine materials. So had we had all 6 operating wheels, we probably would have avoided the collapse into this material. But even with now 2 failed wheels on the rover, just before we had to shut down for the winter, the rover was actually making progress on being extricated. So to answer your question, I think if we had 6 wheels, we never would have been in there. Had we been in there, we would have been out of there in no time at all. And then, do these kind of hazards exist elsewhere on Mars, and is Opportunity a hazard? I keep bugging Ray and the other scientists, with paranoia, think out of the box. Make sure that that there aren't these kinds of things. I mean, there are hazards out there. We just haven't found them, and so we have taken several measures. One of Ray's team has developed a very sophisticated soil physical properties terramechanics model that here hasn't existed before, that allows us to simulate the dynamics of the rover in various terrains. So that's a tool we can use to anticipate problems and to solve problems if we encounter them. But we've also been very vigilant, and remote sensing devices like CRISM and HiRISE provide us with much more geologic information about the terrain ahead for the vehicle, and to use that information to guide the rover safely.
Any other questions? Any from the chat? Okay, that's it. Thank you very, very much for coming and speaking, and thanks everyone for coming and covering this. Our next